Welcome back to the MATLAB tutorial series. So far, we've worked with numerical arrays and matrices, but MATLAB can do much more, including solving symbolic math problems just like you would by hand. In today's lesson, we'll explore MATLAB's Symbolic toolbox to compute derivatives, integrals, and limits with just a few commands. Before we begin, we need a symbolic variable. A variable MATLAB treats as a mathematical symbol instead of a number. Using the command syms_x, we tell MATLAB to create a symbolic variable named x, allowing us to define expressions such as polynomials or trigonometric functions symbolically.
Let's start with a polynomial function, x cubed plus 2x squared minus 5x plus 7. We type f equals x cubed plus 2 times x squared minus 5 times x plus 7 to store it in the variable f. To find its derivative, we use the command diff of f. MATLAB returns the symbolic derivative, 3x squared plus 4x minus 5, just like you would get if you applied standard calculus rules. This is incredibly helpful for checking homework, validating analytical steps, or exploring mathematical behavior.
Next, we compute the indefinite integral, or antiderivative, of the same function. Using the command int of f, MATLAB returns the general integral of f with respect to x. It includes an implicit constant of integration, just as you expect in calculus. Symbolic integration is especially useful for solving equations, analyzing systems, or verifying manual calculations. Now let's evaluate a definite integral, for example, from 0 to 2. We type int of f x 0, 2, which tells MATLAB, integrate the function f with respect to the variable x, starting at 0 and ending at 2. MATLAB returns a numeric value, representing the exact area under the curve between those 2 points. This is perfect for physics, engineering, and optimization problems. Limits are another essential concept in calculus. Let's examine the classic expression sin x over x. As x approaches 0, this expression becomes undefined if evaluated directly, but its limit exists. We calculate it using limit g x 0, where g is the expression sin x over x. MATLAB correctly returns 1, the well-known limit from fundamental trigonometry. This is extremely useful when analyzing continuity or resolving indeterminate forms. Finally, let's compute a limit as x approaches infinity. Consider the rational function, 3x squared plus 1 over x squared minus 2. Using the command limit h x inf, MATLAB determines how the function behaves as x becomes very large. Since the highest degree terms dominate, the limit approaches 3, and MATLAB confirms this instantly. This type of analysis is essential in control theory, asymptotic analysis, and mathematical modeling. Let's summarize what we learned today. We created symbolic variables using syms. We computed derivatives using diff. We evaluated both indefinite and definite integrals using int. We calculated limits using limit, including limits at infinity. MATLAB's Symbolic toolbox makes complex calculus operations simple and exact, perfect for engineering, math, and scientific analysis. If you enjoyed this walkthrough, be sure to like, comment, and subscribe for more MATLAB tutorials. Thanks for watching, and I'll see you in the next lesson.